Hello, I am Matthieu, and today I will present my work on efficient renaming in conflict-free replicated data types, or CRDT, for short. As a PhD student, I am working on data replication techniques in local-first software. Currently, I am focusing on sequence CRDT, which are notably used for real-time collaborative text editing applications. One of the state-of-the-art of sequence CRDT is Rukusplit. In Rukusplit, the elements are ordered relatively to each other using their identifier. Here we have an example of a Rukusplit sequence which contains the element HLO and their corresponding identifier. Identifiers are made of the position, which help us to order the element relatively to each other, and the ID and the sequence number of the node which inserted the element, and finally the offset. In this example, the identifiers are what we call contiguous. They are identical except for their offset, and their offset are consecutive. The main idea of Rukusplit is that in that case we can aggregate the element into a block and store only the range of identifier instead of every identifier to save some memory. And we can still insert a new element into a block by splitting it. In that case, Rukusplit generates the new identifier by using the predecessor ID as a prefix and appending a new quadruplet to the identifier. As shown previously, the size of identifier is not bounded in Rukusplit. As the collaboration goes on, identifiers tend to grow. Additionally, the number of blocks composing the sequence increases as well. This impacts the overhead of the data structure on several aspects: the memory footprint, but also the integration time of update, as well as the bandwidth consumption. To give you an example, we measure the size of a Rukusplit document at a given point, and we found out that 99% of the document is metadata. Less than 1% of the data structure is actual content. So, how can we reduce the overhead introduced by the Rukusplit data structure? We propose a mechanism to reassign shorter identifiers to elements and to aggregate them into blocks in a fully distributed manner. What we propose is a renameable Rukusplit, basically Rukusplit with a rename operation. This operation can be performed without any kind of coordination between nodes, and in this talk we focus only on scenario without concurrent rename operation. So how does this operation behave? We have an example here with node A performing a rename on its local state. So what we do is first reassign a new identifier to the first element. So we use the same identifier as previously, but we update its node ID and node sequence number with the current node 1. And then, for all remaining elements, what we do is we just increase consecutively the offset. This way we are able to generate and assign contiguous identifier for all elements, and then we can aggregate them into only one block to minimize the data structure overhead. Now let's consider a scenario in which another node B, insert concurrently to the rename operation I described before, a new element into its state. If then we try to insert this new element into the new state of A, using its identifier, actually we won't insert it at the correct place. We won't respect the intended order by the user. So we have to deal with this case in a particular way. First thing we have to do is to detect this concurrent operation. To do so, we use an epoch-based system. Basically, the sequence starts at the epoch 0. Each time a rename operation is applied, the sequence moves on to the next epoch, and all operations are tagged using their origin epoch. So when you receive an operation, by comparing the epoch of the sequence to the epoch of the operation, you can detect if you apply concurrent rename operation. If that's the case, you need to transform the insert operation, for example, against the effect of the rename 1. So what we are doing is basically applying some operational transform technique. The algorithm to transform to rename concurrently inserted identifier is described in the paper, but to give you the main idea, what we do is we find the predecessor of the given ID in the former state, in the state before the renaming. Then we find its corresponding new identifier in the new state, the state after the renaming. And finally, we generate a new ID for the new element by concatenating the new predecessor ID to the given ID. This way, we are able to insert the element at the correct position. The downside of this approach is that we cannot delete, we cannot garbage collect the former state as soon as we apply the rename operation, since we needed to transform concurrent operation to rename 1. But it also means that once the rename operation is causally stable, once it has been observed by every node, then we are able to safely garbage collect former state. So let's move on to the evaluation part. To validate our approach, we run some simulation to compare renameable Rukusplit performances to Rukusplit 1. Actually, the first thing we did is to check if the system converge. So we compare the final content of node per session, and we didn't observe any divergence. So, okay, this is an empirical result, not a proof. But still, it represents a first step toward the validation of the correctness of renameable Rukusplit. Then we compare the memory footprint of renameable Rukusplit to Rukusplit 1. In our simulation, nodes are editing collaboratively a document, and the simulations are divided into two phases. In the first one, nodes focus on generating content, so there is much more insert operation than remove one. After a while, they switch to a second phase, which is the editing one. At this point, the balance between the ratio between insert and remove operation is balanced. So, in blue you can see the evolution of the size of the content. So during the first phase it increased and then stabilized during the second one. In red you can see the continuous growth of the Rukusplit document. And then we measure the evolution of the size of a renameable Rukusplit document. And we benchmark two different scenarios. In green is the first one, it's the best case scenario for renameable Rukusplit. In this scenario, as soon as the rename operation is issued, we assume it is causally stable, so we garbage collect the former state immediately. And in this case, we can see that the rename operation helps us to enable us to reset the overhead of the CRDT. On the other hand, the second scenario we consider is the worst case scenario for renameable Rukusplit. In this one, a rename operation never becomes causally stable, so we cannot garbage collect former state. But even in this worst case scenario, we are performing better than Rukusplit. Then we compare the integration time of insert operation on Rukusplit sequence in orange here and renameable Rukusplit 1 here in blue. So basically, as the rename operation enables us to aggregate all the elements into only one block, rename operation reset the integration time, speed up the integration time of future operation. Finally, we benchmark the integration time of the rename operation itself. And here the main result is this operation is much slower to apply to integrate than others. It takes up to 100 of milliseconds to rename a document according to its size, according to its number of blocks. So if we wait for too long, this operation can become noticeable by the user. So our current research trail is which strategy can we propose to trigger rename operation while retaining an acceptable integration time. So, to summarize this presentation, we propose a new CRDT, a new sequence CRDT, renameable Rukusplit, which is Rukusplit with a rename operation. To deal with concurrent operation, to rename one, we define some transformation function. Currently, we are working on implementing the first version of the transformation function to deal with concurrent rename operation, and we are proceeding to its validation. We are also working on different strategies to trigger efficient rename operation. What is left to do is to prove formally the correctness of renameable Rukusplit. And finally, we can see this work as a motivating example of how OT technique can be integrated into CRDT to build a more complex or efficient replicated data type. So it will be interesting to investigate this combination of technique in a broader setting. Thank you for your attention. Do you have any questions?